Hello everyone, how's everybody doing? Hope you're doing fine. I'm doing okay. My age, I get arthritis, and that's what I have, and that's what I have to deal with. Anyways, want to say that first, we put out the book. It's known as the Rope Hypothesis. You can go and check it out at ropehypothesis.com. You can download it. It's a 160-page book for free. You can look at it and come up to speed on the rope model of light and gravity. And for those who have a second language and are good at it, we encourage you to contact us at hotmail.com if you want to translate it into your other mother tongue or whatever. Okay, so if you're good at translating something into some language, please contact us. And we had a couple of people. One is already apparently translating into Hungarian, another one into Indonesian. So, and I'm translating into Spanish, so maybe we'll get this book all over the world. Anyways, the other thing I want to mention again is that we have a conference coming up in Lusaka, Zambia, and it's hosted by my friend McShamus, and Seamus. I call him Shamu. And beg, borrow, and steal, and see if you can make it, because it's going to be maybe a trip of a lifetime, okay, or the adventure of a lifetime. I hear there's beer down there, so I'm going to try it. Anyways, getting back to our subject matter. The other day I left off and I mentioned in passing some nouns that we have in physics, in mathematical physics, really. And you'll see a list here. This is just an impromptu list off the top of my head. Words like orbit, energy, mass, trajectory, we consider those nouns in ordinary speech. And mathematicians use them in their language, in their mathematical language. They use these words as well. And so what I want to say is that these are not nouns for the purposes of physics. The way we look at it in rational physics, all of these are verbs. That's why they're in green instead of brown. Those are the colors I chose to separate nouns from verbs. Here's another list, similar. These are words that are not verbs, but they're concepts. Some kind of concept, either static or whatever, typically static concepts in this case. And again, they're treated as nouns. People use them as the subject of a sentence, and that's not allowed in rational physics, okay? And what's the problem? One of the big problems with this is that people tend to apply the wrong adjective or the wrong adverb. They apply adverbs, they end up applying adverbs to nouns and adjectives to verbs. That's what we end up having. So, people talk about infinite motion or constant, what could it be? A constant orbit or whatever. And, you can't do that. You got to use these words consistently, right? And you can't mix them around. And so this is a serious problem today, because you wonder how we got to general relativity saying that time dilates. And you say, what do you mean time dilates? Well, time is not a physical object. It's not a noun. Only objects can serve as nouns in rational physics. And for someone to say that time dilates, or that gravity bends time or warps time, or that I transfer energy. These terms are all irrational, and all that language has got to go. All that mathematical physics language is no good. Okay? So that's one of the issues, a major issue. People say, Bill, you're doing semantics, you're boring me with this. Unfortunately, we have to bore you. You need to understand the language, because that's when people run into trouble. And I have an example, a good example today. Someone wrote a comment, and I thought that comment needed to be highlighted, brought in, so that people can see how this new language that we're proposing in rational physics, rational science, is applied. Okay, and here's the case. Person put this comment in there, okay, and he says, the lines of force are real, okay? We can see and feel it. I don't think you can see or feel the lines of force, right? The people, not the people, but the entities that have some kind of interrelation with them are the iron filings. We can see those, but we can't see the lines of force that compel iron filings to line up in certain patterns. How can it not exist? It is certainly not physical, but it's real. It's not physical, but it's real. Okay? Is it so heretic to have this notion that something non-physical actually exists? Then he continues, he says, if yes, we are denying the existence of what light are homes and power are motors, electricity. And so, I think what's happening here is this fellow's chasing his tail around because he doesn't define his terms. So what we do is we define them, and then we know what we're saying, what we're talking about. And we define first physical, the word physical that he uses, as that which has shape. That's physical. Okay? So that's the definition we use for the word physical. Then exist becomes anything that is physical. It has to be physical. It can't be a concept. It's got to be an object. Okay? It's got to have shape, which is the only criterion for physical. And then it's got to have also location, the set of distances to all other objects in the universe. Now we can use the word exist and physical consistently, and we don't get into this this run around this fella had, what I call dog chasing his tail around. That's what he did. Okay, so I hope he stops chasing his tail around and follows, a little bit of semantics that we propose, so that we can apply it to analyzing what he's trying to say there. Because he goes back and forth. He says, first he says we can see and feel it. And we're saying, as you can see on the bottom right, we don't use the senses at all. So anything related to senses has nothing to do with the word object or with the word exist. The word exist has to do with physical presence. It only has to have location. We do not need to touch it or see it or smell it or taste it or whatever. Okay, we can't taste light. We can't smell gravity. Okay, so anyone who thinks that they're going to zero in on the causes of gravity by applying the senses is mistaken. These are invisible, intangible things. Okay, the mediator of gravity is invisible and intangible. So you can't go to the lab and say, I'm going to run an experiment to find out what gravity is. You won't. The way you do it, you sit back, right? You have a mate, maybe like I do, You sit back and you think. You try to visualize. Then you can figure it out. Because that's all you need to do. You need to figure out what invisible mediators, Mother Nature, Father Universe, God, whoever out there, is using to do gravity, light, magnetism, etc. All the invisible stuff in the universe. That's all we have to do. Once we figure that out, we're done with physics, because now we can see the universe, we can visualize the universe. Okay, maybe not see it, but visualize it in our minds. Okay, and so yeah, we have a little bit of a problem with the language. That's where it starts. And let's see. Let me put this up here. This is then a reply to him, and that's what people want to really understand, try to get to the bottom of. What are those lines of force? Well, we sprinkle iron filings over magnets, and they leave these patterns that we see there. Okay, and the question is, there's something out there that we can't touch, we can't see, we can't smell, we can't taste, that is moving these iron filings around immediately. It's just like snap right there, you know, and instantly they form around these patterns around the magnets. And you can see that they form specific patterns. I labeled them as concave and convex in the book. Okay, these are pictures from the book. And they have to be real in the sense that, you know, they cause effects in the physical world. And you can see that at the bottom right. That's a solenoid or a coil, bed spring, whatever you want to call it. And it's a live one. And you can see the lines of force going around. Okay, so they're circling the entire coil. Okay, and they circle in specific ways, just like the magnet above it. If we were to place the magnet on top of that coil, it would have exactly the same pattern. In other words, what you're staring at the bottom right, which is a coil, is also a magnet. Okay. And the lines of force had better be real because they cause a force right through the center of the coil. And it also has its north and south. And so what is that force? I mean, are we going to put spirits in there? Are we going to do it with angels like Thomas Aquinas did? You know, what's going on there? What is that invisible stuff? And if you say there's nothing there because you can't see it or touch it, then in effect you're putting spirits in that same, you're doing black magic. You're doing voodoo magic. You're saying, no, there's nothing there, but suddenly that nothingness, those angels, those spirits, whatever you call those, that X, that's pushing things through there. It's causing a force. And you're saying that's caused by nothing? There's nothing there just because you can't see or touch it? And that's when you have to define the word object not as that which you can touch or see, smell, taste, hear, right? You have to define it as that which has shape, which is the only property all objects in the universe have. And the word object is a synonym of the word physical. So they're both synonyms as far as we're concerned. And that which is physical is not that which you can touch or see, like in ordinary speech. In rational science, it's that which has shape. And if there's something that has shape in there, or like James Maxwell said, in that space, talking about a magnetic field, he said, there's matter in motion. Some kind of exotic matter that can't be touched or seen, and it's in motion in there. It has an effect on our real world, and we say, well, we can't see it or touch it. Yeah, you can't, because that's not the definition of what an object is. Shape is what characterizes an object. And until you get that in your head, you're going to have a lot of trouble, especially in this channel. Okay? Okay, so where does this take us? Well, it takes us to the subject matter of today, which is Mr. Aristotle and Mr. Euclid. And they lived about 2,000 plus years ago. And one of them, you know, Aristotle, he tried to do physics. He tried to do physics. Not that he did, but he tried to do physics. What he did was define the word physics, okay? And this is what he was up to. He's trying to lay the foundations of physics. And he used nouns such as, you know, stand still or at rest, location, distance. These are the nouns that he's going to use. Okay, and he's going to talk about motion, time, and number, none of which qualify as nouns for the purposes of rational physics. But this is the starting point, one. And second, this is what the mathematicians today have inherited from Ari. Okay, so good old Ari used these nouns. Then he used these qualifiers, these adjectives. And again, you can see that if those are not nouns because they are either dynamic or static concepts, then these become incongruous, because now you're applying an adjective to that which is not physical, to that which is not a noun, to that which is not an object. Okay, so now you're talking about an infinite motion, or for example, or whatever, in between two numbers. You know, you can't use those terms in physics. There's no physical object called number. And then you cannot talk about something being between two numbers, not in physics. In ordinary speech and mathematics, yeah, you can say all that, but not in physics. Okay, because you're no longer using objects. Physics is mediated by objects. You can say between the table and the chair, but you cannot say between energy and mass, for example, right? So this is the issue. The issue is you got to be very careful with the language, because we're going to spot all this stuff, and once you get the good thing about it is once you master the language and you say in whatever paragraph you read out there, from ordinary people, from high-level people, it doesn't matter. You read it and say, well, what is the noun? Well, the noun is the object. What is the object in this sentence? Not the noun, not the noun or the thing you're going to talk about, but what is the real object here? The thing. And when you start looking at that and you say, well, where's the verb? Where's the adverb? Where's the adjective? Then you start realizing how how the ordinary speech cannot be translated directly into physics. Okay? And in contrast to him, we have this other fellow, and his name was Euclid. And for short, we call him Euk. And Euclid, he dealt with other kinds of nouns because he was trying to do geometry. He was trying to lay the foundations of mathematics. That's a little different. And his nouns, he used words like point, line, plane, solid, and also number, because he's going to do things with numbers, right? And the qualifiers he uses are things like angle, perpendicular, parallel, missed an L there, center, edge. These are the words he's going to use. So these two fellows are going to use two different languages, and you have to remember that the guy who defines the word physics is Aristotle. Now, maybe this word was used earlier than that. Physics just means nature. It's related to the word nature, so it's like the study of nature, that sort of thing. And he's the guy who defines physics, the word physics, and he's going to apply it more or less like me. He's going to try to get to the foundations. He's trying to figure out how this universe works. And that's not what Euclid's going to do. Euclid's going to set the foundations for geometry. And before we can get there, it's important to try to put this in the right historical context, which is what I want to do today as a starting point. This will be an introduction to geometry, to what comes later. But what I want you to note is how this developed, especially at its starting point, which was around the time of Aristotle and Euclid. It really started earlier. These two individuals inherited a lot of this. They developed it a little more. Perhaps they put they had their inputs into this, but essentially they inherited a lot of that from maybe 200, 300 years of people like Thales and Pythagoras and so on, who develop a lot of stuff and pass it on from generation to generation. By the time it arrives at the 4th century BC, which is when these folks lived, Aristotle, in 3rd century is Euclid is credited. We don't know when he was born, when he died. Okay, we know a little more about Aristotle, even though Euclid came a little later. But let's put them in the proper context. And here's the little map so that you can get a feel for where these guys lived and what they did. Athens was the center of the world in those days, around 300-400 years BC, until the Romans finally conquered them. And Aristotle was not an Athenian. He was not from southern Greece. He was from northern part. He was a Macedonian. Okay, and he studied with Plato, who had set up his academy in Athens. In fact, north of Athens, he was outside of the city limits. That's where the academy was, north. And Aristotle studied there for 20 years until Plato died. When Plato died, Aristotle goes back, I guess, to Stagira, where he was from, or perhaps directly to where he was going to go next, which is Pella, which was the capital of the Macedonian Empire, which had just started. Philip II, Alexander the Great's father, he called Aristotle to be the tutor of Alexander, and that's what his job would be for the next couple years. And by this time, Euclid probably wasn't even born. because Alexander eventually goes out and conquers Persia. And before he does, he obviously has to get rid of his dad. And apparently that was, something that, happened, one of those lone gunman type of crimes. Someone killed Philip, and more than likely it was orchestrated by Alexander's mother. Why? Because Philip had taken a new bride, had a boy with her, and this other fella kills Philip, and then they kill him immediately. So dead men tell no tales, sort of thing. And that's how Alexander becomes king. As soon as he becomes king, since Aristotle was his friend and educator, his tutor, right, his professor, Aristotle goes back to Athens, but this time he doesn't go to the academy, to Plato's academy, because he didn't really like a lot of the ideas coming out of Plato, and instead he goes and to the Lyceum. The Lyceum already existed. People gathered there, philosophers, soldiers, vendors, everybody gathered around the Lyceum, and the philosophers met there, and now that Alexander is the head of the entire Greek Empire, right? He sends Aristotle there. Aristotle puts his headquarters at the Lyceum. He teaches there, and he has a lot of students. And that's why one of the issues that comes up today is whether he came up with all these ideas or this was a collective effort. Maybe Aristotle was giving lectures and his students took notes, and maybe those are the notes we get today. It's very hard to know exactly how his book called Physics got assembled. But we give him credit, and I guess in the end it's irrelevant. The important thing is what he says in the book. Okay? Now it turns out that he was there for like 10, 11 years, and then Alexander gets murdered. And yeah, I mean, another case there, because Hephaestion, his right-hand man, he died a few months earlier in mysterious circumstances. He got sick all of a sudden, probably poisoned, and I think that's the same thing happened to Alexander a few months later. They got rid of them, and because he was getting rid of a couple of the generals, and the generals just took over the empire and divided it up. So that's in a nutshell what happened. Well, when news reaches Greece that Alexander was dead, Aristotle was in a little bit of a trouble because he was a Macedonian in Athens. He was not a citizen of Athens. And city-state citizenship was very important. It was like, you're in a different country, so to speak. And so Aristotle is there. He's got to run for his life kind of thing. He realizes his situation. He leaves Athens. Maybe he was to some degree the eyes and ears of the Macedonians in Athens. He's got to leave. He knows this. So he leaves, and, it's very, he dies about a year later. So, again, maybe he was murdered for all I know, who knows. But the point is he leaves, and that's the end, essentially, of the formal Lyceum. Later on continues a few more years to the 3rd century, I think to the 280, 250 before that, before Christ. And finally, just dwindles into nothing. Finally, it's destroyed by the Romans many years later. And so this is the story for that. And the question is now, where does Euclid come into this? Well, Euclid is one generation right after Aristotle. He's one generation later. He's like 20 years younger than Aristotle, at least. And he studied with the students of Plato, which were at the same age level as Aristotle. So he comes later. And in fact, he goes to Alexandria, to the city north of Africa, in Egypt. Let's see if we can put that up again. He's right there in Alexandria. He goes there, and Alexandria is founded by Alexander in around 330, 331 BC. So he goes there like 10 years later. Euclid goes there about 10 years later, and he's brought in there probably by Ptolemy. Okay, Ptolemy was the one of the generals that took over the empire, and he took over the area known as Egypt. Last of his dynasty would be Cleopatra many years later. And he probably brought Euclid over. He probably realized that Euclid was a smart mathematician. He said, I probably have some use for you. And Ptolemy himself, he was into astronomy, all this other stuff as well. He liked science and the arts. And so he brought him over. And so the issue is that Euclid probably studied I don't think he studied at the academy. I don't know if it was open at that time, but he certainly studied at the Lyceum or got to know Aristotle if he lived in the same period of time, because that was the University of Athens essentially. Okay, and all the smart people, all the rich kids who wanted to get educated, they would go into the Lyceum and get educated. So Euclid was very familiar with at least the ideas that Aristotle put forth. And he's going to use a phrase that he's going to include in his book Elements, which is that which has no part, referring to the point. And we find that in physics as well, Aristotle's physics. He already mentions that which has no part. And it's like Euclid just took that with him. So I have to suspect that Euclid really studied in the Lyceum, or at least was very familiar with the Lyceum. He probably went there every day or whatever. Okay. Anyways, so again, Euclid does mathematics, and Aristotle tries to apply all these concepts to physics, what he understood to be physics. And what are the things that he introduces? Again, things such as distance, time, motion, these abstractions, but all related to how the universe works. That's not what Euclid does. He applies it to geometry, to planes and solids especially. He analyzes that in quite a bit of detail in his book Elements. Okay, so here we see how they each apply it. Here we have Aristotle. He's trying to, he's looking at distance. Okay, he's not interested in using geometry per se. Okay, so he's just trying to look at things like distance, motion, etc. And actually, this is really more like motion. Okay, because he's looking at how things move between his hands. He's trying to analyze that, and obviously when he analyzes that, he gets to not only distance, which is really distance traveled, measurement. He gets into motion, and he gets into time. He says, "Oh, hold it! It takes so much time, and what's in between these two balls? Any two balls that you selected, dots or whatever you want to call them." So he gets into these kinds of analysis in his book Physics. He wants to get to the bottom of what is distance, what is motion, and what is time. So he has to introduce terms such as continuous. Okay, that's and in between. These are important terms for him because he's trying to define them, which is good. I think it was good. The only problem, he applied it to concepts. He didn't apply it to physics, and that's I think where he failed. But I think he had the right intention. And again, he's the first guy who starts this all. And you can expect anyone who starts something to make many errors. And I think he set physics on the wrong path from that point of view. But at least he tried. I think he at least was very interested in getting to the bottom of things. And here's Euclid in comparison. What does he look at? Well, he looks at triangles. So he's not looking at distance per se. He wants to analyze angles and relations between the sides and etc. Okay, and that's what geometry becomes. So what happens next? Well, Ari applies his so-called distance, time, and motion, but this time he's going to replace it with a line. Okay, so he's going to use the word line. He is going to use that. Okay, and that's not what Euclid is going to apply it to. Euclid is going to apply the line to his, to the edges of a plane, for example, a triangle or a square, or maybe even the circumference of a circle. Okay, Ari, what he does next is he turns them into points. Okay, because he says, look, we have all these motions of something from one hand to the other. and we chop them up in locations, and we're going to put a point in each one of those locations. So he's thinking of in terms of motion. This is what he's trying to analyze in his book. He wants to analyze, location, distance traveled, motion, and time. What is Euclid going to apply it? Well, he's going to apply the same thing. He's going to say, look, we're going to turn this line into a bunch of dots, and a line is made of points, okay? And then the question was, the issue of continuity and whether they were, they were continuous, or whether they were one right after another in the sense that successive, right? Like if something was flowing. But that was more a term that Aristotle applied more than Euclid. And yeah, what they're going to do, first, Ari, he's going to replace that with numbers. So the location becomes a number. And so now we're talking about numbers rather than about physical things. He's going to try to see if he can, he constantly introduces the term unit, referring to numbers and saying, there's like a space between two units, like what is between a 1 and a 2? Well, if they're integers, well, there's nothing in between there. It's like if these are just integers, there's nothing between a 1 and a 2. So he uses arguments of that nature to show that there is, under some circumstances, discontinuity, okay? And Euclid's also going to replace them, with numbers. He's going to be dealing in geometry. He's going to introduce numbers, and he's going to replace the locations first with a dot, which he calls a point. It's a zero-dimensional, no-volume point, and that point really represents a number. Okay, that's what it is. And so this is the starting point for humanity. Essentially, or for the Western world at least, this is where we got our start in so-called physics and mathematics. And it's interesting how Aristotle eventually ends up defining what he means by physics. Because this is an important point, because if the mathematicians today have changed that, well, they should call whatever they do something different, not physics, because they're not doing physics. Not according to how Aristotle, originated it. And these are the notions that Aristotle had in mind when he created physics. He says, what does physics deal with? And he says it deals with of things that exist. I like that first statement. Things that exist, yeah. Totally in agreement. And that's not what mathematical physics deals with. They don't deal with things at all, let alone things that exist. They talk about space-time, and they talk about particles, and you say, well, a particle, that's a thing that exists, right? No, because a particle is a vibrating field or a bundle of energy. And what is a field? What is energy? A concept. So they're not dealing with things at all. So that's important to note. That's how Aristotle started, but we changed that. In other words, a mathematical physicists changed that because they said, look, we don't deal with things because we can't deal with things. We can't explain how Mother Nature runs her universe with things. The only way what we can do is describe. And the way we describe it with numbers. That's the language you got to learn if you want to learn so-called physics. And what they mean by that is mathematical physics and not physics. Physics is this, what Aristotle laid down. He says of things that exist. That's perfect definition for physics. And he says some exist by nature and some from other causes. Okay, again, he's talking about causes, and he's thinking, I'm sure, mechanisms. That's what he had in the back of his mind, which is what we're about. Okay, and then he tries to define what he means by nature. He says, one account of nature is the immediate material substratum of things. In other words, what things are made of. We call it mereology, and we dismissed all that completely. So we disagree with Aristotle here. What things are made of is not important. What we want to do is see the mechanisms that these invisible things do, how they do it. Okay, that's what we want to understand. We don't care what they're made of. Okay, what we care is what is the mechanism. It's like saying I showed the other day. Was it Felix the cat breaking the window? Right. So you say, how did the window break? Well, it broke because a brick went through there or a horseshoe or whatever. And what Aristotle says here is, well, let's look at what the horseshoe is made out of. Let's look at what the brick is made out of. We don't care. That doesn't has nothing to do with the mechanism of how the window broke. The mechanism of how the window broke is straightforward. Brick goes through there, breaks it, and brick is on the ground, and the glass is all shattered. We don't get into what is the glass made out of. It has all these particles. Is it SiO2? Is it strong? Is it weak? We don't care about any of that nonsense. We just want to know how the window broke. And that mechanism is brick goes through window. We're done. That's it. That's how kindergartenish it is. And it's when you get into all this stuff that is unrelated that we get into trouble. And that was part of Aristotle's failure, I think. Anyways, he says, another account is that nature is the shape or form which is specified in the definition of the thing, which is very close to, I don't think he really had a total grasp of that. He was not aware of what he said. But yeah, we have what is the thing made of, and then its form. That's it. Those are the things. And those are the things that exist. And I guess he had this notion also of see and touch, maybe in the back of his mind, And obviously they couldn't see the air, and so that raised a lot of questions. They couldn't see gravity, whatever gravity was causing, the stone to fall to the floor. They couldn't see that, so they said, they couldn't figure that out at all. They weren't even close. And then he says the mathematician differs from the physicist. Aha. Physical bodies contain surfaces and volumes, lines and points, and these are the subject matter of mathematics. In other words, he dismisses lines and points per se as geometric objects, and he says, that's the realm of mathematics. They like to talk about volumes, angles, whether something is perpendicular or parallel. That's the subject matter of and the numbers, obviously. That's the subject matter of mathematics, geometry, essentially, which was I think the cradle of mathematics. And it's not what he's trying to do. He's trying to understand nature. He's trying to understand how things work, mechanisms, causes. And that's why he begins at things that exist. And I think this is an important point to start, because you need to keep those two separate. You need to keep the mathematician very far away from the physicist. And that's not what mathematical physics does. They try to do the opposite. They try to merge these incongruous worlds. Math is a language, and physics is a science. Math is not a science. Math is just a language. And like I was saying the other day, is these people, the mathematical physicists, are trying to tell you that in order to understand how this universe works, you need to understand Chinese. You need to take a very advanced course in Chinese. So I need to learn Chinese to understand how this universe works? Yeah, you do. And can't you translate it to English so that I know how this universe works? Well, it's not a one-to-one correspondence. I can't. It's not a literal translation. And so we can't do it. Well, give me a ballpark figure or a big ballpark idea. And that's when they come in, they say, well, you have this four-dimensional space-time, which is unimaginable, and the bowling ball weighs down to the fishnet, and anything that falls in there is gravity. And that's our explanation. So, yeah, but hold it, but time is a concept. You're going to bend time? Well, that's why you need to learn Chinese, because I can't translate Chinese directly into English. And they go around in circles. They think that because they have a language called mathematics, that you need to understand this descriptive language in order to explain a mechanism. And that's absolutely not true. But that's the notion people have out there. And so this is where it all starts. It starts with Aristotle, followed by Euclid. Euclid goes into geometry. He essentially, you can say, lays the foundations for mathematics, even though mathematics already existed before that, came from way back when. And Aristotle, he goes in a different direction, and he's trying to figure out how this universe works. And then what you have is people throughout the ages, we talked about Aquinas, St. Thomas Aquinas, he picks up from Aristotle. He picks up where Aristotle left off and tries to figure out again what motion and specifically time. They're concerned with time by this time. By the 13th century, they're concerned with time. And mathematics of geometry really takes off in the 17th century when people like Huygens and Newton, Leibniz, these guys pick up on that, they develop it further, they invent the calculus and so on down the line. And so they take their cues really from the side of Euclid. They're not interested so much in understanding. They want to understand, but they touch upon Aristotle lightly. They go more with what they consider something more organized, more precise, something you can count on, which is geometry, which is mathematics. Okay, so that's it for today. What I'm going to do is I'm going to continue with this line. I'm going to continue with Aristotle, analyzing a little bit of his book, compare it against Euclid so that you can see the contrast between how we started, the Greeks, and you're going to see a contrast between Aristotle and Euclid, especially on what they're trying to achieve, each one in his own realm. And by the way, Euclid was more from the line of Plato. And Plato was a mystic. He was a guy who all the religious folk like St. Augustine and even St. Thomas, all these people, they were Platonists, Platonists, okay? They followed Plato. They liked a lot of the, shadowy stuff. The real thing is not the thing, but the shadow of the thing, that sort of thing. And so they were mystics. And that's the line that Euclid is really going to go into, because he goes into all this abstraction of geometry, which is what we have today. When you look at geometry, it's all abstract, and all mathematics is quite abstract. It's all out there, in numbers, and you just have to look at relations. All that is abstract. It has nothing to do with our real world. A ball falling, or a seesaw, or all these physical things that we see every day. So one thing is the mathematical description, another one is the mechanism, and its mechanisms which died essentially with Aristotle. Okay, so we'll see you, on Sunday? On Wednesday. We'll see you on Wednesday, and we'll continue with this line of thinking. We'll see you then. Bye-bye.